All right, today we're going to talk about chemical reactions that occur with unsaturated hydrocarbons, alkenes, and alkynes. Alkenes and alkynes tend to undergo addition reactions. So let's look at let's start with a very simple alkene. All right. So first of all, let's name the alkene. Tell me what the alkene is. This is ethene. All right. And ethene will react with a halogen, let's say chlorine. The halogens are those elements out of group 7 or group 17, A, depending on which numbering system you're using on the periodic table. Or group 17, I should say, group 17. All right, so again, just a reminder, elements that occur diatomic in nature are these elements. And you'll notice these last ones here. Oops. Okay. Chlorine, iodine, fluorine, and bromine. These are halogens, and they all are diatomic in their natural state. All right. So we have chlorine, a halogen, and what happens here is the double bond opens up. Now, the double bond, I don't think the book does a good enough job describing this, but if you go back, we were looking at, and I think they do this because this is just an introductory course, and when we talk about bonding, we can have the p orbitals can overlap one another like so. And when these two, and again, it depends on the bonding theory you use, whether you're talking about hybridization or just atomic and molecular orbitals. But you can have bonds that occur in line with the carbons. This is called a sigma bond. And you can also have bonds, and I'm going to exaggerate these. I probably ought to exaggerate them even more. But you can have bonds that occur maybe with a p orbital that are off center between the two carbons, and there's an overlap here and an overlap here. These are called pi bonds. Pi bonds. So in a double bond, you have a sigma bond and you have a pi bond, and that's why we have two bonds here. And remember what a bond is it's the sharing of electrons. So one electron from this carbon, one electron from this electron are being shared, and then one electron from this carbon, one electron in line with the carbon axis is also shared. That's a sigma bond. So with unsaturated hydrocarbons like ethene here, when we apply or we add a halogen gas to this substance, which is also a gas, remember ethene is a gas, it causes this pi bond to break and to open up. And that allows for an addition reaction to occur. Now, what an addition reaction is you've added something that wasn't there before. So not only do you still have the two hydrogens that you had before, you now have two chlorines added to the substance. So this is called an alkyl dihalide. Alkyl, because remember we said this could all be one group here, an alkyl group. It's not, if we had all hydrogens, it'd be a saturated hydrocarbon, and we would call it and it is an alkane. But so we've gone from an unsaturated hydrocarbon to a saturated hydrocarbon, and this is called an alkyl dihalide because it's two halogens attached now, two halogen or halide groups, chlorine here and chlorine here. So we would call this 1,2 dichloroethane. So we've gone from ethene to over on the reactant side here to ethane, dichloroethane. 1,2-dichloroethane. So this is called an addition reaction. An addition reaction. All right. And where does the addition reaction occur? Well, it occurs where the double bond is. It occurs where the double bond. All right. So we can make you can make it as complex as you want to. You could do a line structure like this. And you could say there's a double bond here, and so let's have you name this substance. That's not the best drawing, I agree. All right, so what do? You start here and you go 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's 9 carbons long, or if you've gotten the hang of it, you can just say 2, 4, 6, 8, and there's 9 right there. So this is nonene or nonene. Nonene. You say, why nonene? Well, it's got a double bond. It's an unsaturated hydrocarbon, monounsaturated. That's what we would say here. And so we need to tell people where this double bond occurs, and you always got to use the lowest number for that. So this is carbon 1, 2, 3, 4. So it occurs at carbon number 4. So we would say 4-nonene. All right. So we know that at this point, this is going. If we add something like bromine to this, that bromine being a halogen is going to cause this double bond to open up. So we do the same thing. Again, 2, 4, 6, 8. There's 9. And now this double bond here opens up, and we get a bromine attached here. And a bromine attached here. Okay, so we've added bromine. We've added bromine to these 2 carbons. So this would be our product, and so we need to be able to identify this product. Well, again, it's an alkyl dihalide. This would be, we would look and see this is carbon 4, this is carbon 5, so we would say 4, 5 dash dibromo nonane. All right. So this is an addition reaction. Because you've added, here's a reactant, you've added that to the chain. All right. So let's go to the next slide. We can get more complicated. Let's start off with something a little easier. We could try an alkyne, and our favorite alkyne is ethyne. But remember that's a Y. Or the more common name, and most people call it this, it's acetylene. All right. Either way, you got to be careful. If they ask for the IUPAC name, you'd say ethyne. All right. So the same thing happens here. The difference here is that you have 2 pi bonds. This is actually a pi bond here, and this is a pi bond here below the plane, or it's not in the same plane as the axis between the 2 carbons. And then in the middle here, this bond here in the middle, that would be a sigma bond. So you've actually got 2 pi bonds that can open up. So what that does for you is that instead of adding just 2 bromines, you're going to add 4 bromines. So bromine's going to attach to the carbon here and here. And then on this carbon, the same thing. And so that's your product. All right. So again, we've gone from an unsaturated hydrocarbon, an alkyne, back to a saturated hydrocarbon called, that's an alkane. This would be 1, 2, or 1, 1, 2, 2, tetrabromoethane. Or in this case, you could just say tetrabromoethane. Tetrabromoethane. All right, tetrabromoethane. That would be the best name for this. Because you only have 2 carbons, that's all you can have. Tetrabromoethane. All right. So you're going to see me do that a lot. I'll first start thinking 1, 1, 2, 2, things like that, and then you kind of start distilling that down to what would be the simplest way to name this compound according to IUPAC. All right, so those are the halogenation addition reactions of a saturated or unsaturated hydrocarbon. So that we got to speak the language. This is an addition reaction because we're adding this. Another thing here is this reaction's not balanced. To balance this, we should put a 2 here, and that's generally going to be the case. You're going to have to put 2, a coefficient of 2 in front of the halogen, the diatomic halogen. All right, so now we've got a balanced chemical equation, and we would call this the addition of bromine to ethine, or again, addition reaction with a unsaturated hydrocarbon. All right. Reactions get a little bit more interesting. This time, we're going to go back to our nice double bonded carbon. Now, I'm going to do something a little differently here. I am going to put R's instead of hydrogens. These are alkyl groups, or they can be aromatic groups as well, but R generally stands for something like, R could be, instead of writing out an ethyl group or a propyl group, I can just write R. All right. So depending on what these R's are, that can depend how long the chain is and what the name of the compound is. So this is just a general equation here that we can use. And instead of adding halogen to this compound, we're going to add water. And instead of writing water as H2O, we want to see something structural here. So we're going to make water look like this. Okay? Now, when we add water to an acidic solution, so that means we've taken this unsaturated hydrocarbon, it's an alkene, we mix a little acid with it. It can be, maybe a strong acid like sulfuric acid or nitric acid, although that could cause another reaction. But so sulfuric acid probably a good choice here, or hydrochloric acid. But this hydrogen ion acts as a catalyst to cause this reaction to occur at a faster rate. Remember what a catalyst does? It lowers the activation energy. Let's kind of go back. This is something from Chemistry 140 or 104. Normally on a reaction, if it's exothermic, you have to overcome this hump called the activation energy. So like from where your reactants start to the top of this peak is the activation energy. And that has to be overcome before the products down here can be formed. So this is my products and this is my reactants here. This is time and this is energy. What a catalyst does is it alters the mechanism of the way the reaction occurs, so it lowers the activation energy, and it allows this reaction to become product at a much faster rate. So that's what this strong acid, hydrogen ion, does for this reaction. So think about, what do you think is going to happen here? How do you think this is going to work? Well, it pretty much works just like it's an addition reaction, so it's going to work pretty much just like what we saw before. The double bond opens up. Now, the R group goes here and an R group goes here. and our group goes here, and our group goes here, and then a hydrogen goes here, and the hydroxyl group goes there. So what have we done here? What kind of compound is this? You should be able to identify it. If you can't, you're in trouble, because you should be able to tell me by looking at this general equation. Yeah, you can't tell me it's ethanol because there's these R's attached. If there's a methyl group here and a methyl group here, this is a 4-chain long methyl group, and then you could have a methyl here and here, so you'd have like something like dimethyl bute, since it'd be a 4-chain. If this was a methyl and this was if the bottom here is a methyl and this is a methyl up here, you'd have a 4-chain long group, and so this would be butanol. So what you get here is an alcohol, and that's what you need to be able to identify. You go, oh, I did, yeah, that's a C. So you go, well, how am I supposed to know that? We'll go back to chapter 10 and look at those functional groups. I said that was a really important part of chapter 10, is that you can see what functional groups are attached to the carbon chain, and that's going to determine the properties of that substance. So you know alcohols, they have the OH group, and so when you see this OH group on a long carbon chain, or carbon chain, you're going to have an alcohol. So it's really important that you be able to identify what type of compound this is. All right? So again, this is an addition reaction. And that's what we're going to see a lot of times with these double bonds or triple bond. The bond opens up, whatever we're reacting it with, along with maybe a catalyst required, the hydrogen ion in this case, to cause this reaction to happen. And now we have more things added to the carbon than what we had before. That's why we call it an addition reaction. All right, so now I want to get into something a little more complicated, and this is going to illustrate a rule that you must memorize called Markovnikov. Yeah, let me see. Let me. Markovnikov addition. Must memorize this. I still remember this when I was in college, and it's been a long time ago. So the way your book says it is the rich get richer. My professor used to say, them that has gets. Them that has gets. So what is a Markovnikov addition? All right, so let's start off with a structural formula. And since we're talking addition, you're probably thinking, well, and we're talking about unsaturated hydrocarbons. Let's put a carbon in here like so, and we know a hydrogen has to go here. We know a hydrogen has to go here. And that's 4 bonds on this carbon, 4 bonds on this carbon. And then we'll put another hydrogen here. So we have this substance, all right? So name this substance. Name it. Well, you go, it's 3 carbons long. Doesn't matter whether it's on this double bond, it's here or here. I mean, it'd be the same compound, just be flipped. And so what's the name of this substance? Propene. Propene. Now, you're going, I never have heard of propene. Well, maybe so. There is a common name for it. It is propylene. Maybe you've heard of propylene glycol or something like that. So this name is important too, and this is where we get into, it's kind of hard, like in biology. You're definitely probably going to hear this called propylene. It's an older name for it. It is still used very much today, just like propylene glycol. But the IUPAC name for this would be propene. All right, so we're going to add water to this again. And I can write it this way, just like we did before. And in order for this to react, what do we have to have? We have to have a strong acid. And so that's going to act as a catalyst to cause this reaction to occur. All right, so tell me what the products are going to be. Well, this double bond's going to open up. So I'm running out of space, so I'll write one up here. So the double bond opens up and a hydrogen attaches here. Double bond opens up and a hydrogen was here, and we get an OH group up here. And if you say, well, I don't like it that way, that's fine. Some people ask me, does it have to go, where does this hydrogen and hydroxyl group have to be? Let me change that. We can do that. No problem. Let me see if I can do it this way. No, it's not going to be nice to me. Let's go down here. All right, I'm going to put the hydrogen up here, and the hydroxyl group here. All right, so the hydrogen from the water, one of them goes here. The hydroxide goes there. The double bond is now gone. And then on the end here, we have our methyl group. All right. So that's one of the two compounds that can be formed. You say, what's the other compound that can be formed? Well, let's draw it again. So we have a methyl group. We have CH2. Now watch what happens here. Oops, I've messed up. I've messed up big time. Yes, I just caught a mistake. All right. So you say, well, are you going to edit this? And I'm going to go, no, not today. I'm not. Let's just erase this. Did you notice I added an extra carbon to the compound? It's no longer propene or propane. It's, it was butane. All right. So, yeah, I should have kept that other carbon. All right. So let's go up here. So the double bond opened up here. We got a hydrogen attached to this carbon, and we got a hydroxyl group attached to that carbon. All right. And so this is what we get. And the other possibility is that instead of the hydrogen attaching to the central carbon, the hydroxyl group attaches to this carbon, and the hydrogen attaches itself to this carbon, the end carbon, like so. All right. So again, what's happened here? We had a double bond between the second and third carbon in propane. This double bond opened up. In this one, the hydrogen attached to the central carbon, and the hydroxyl group attached to the end carbon. And in the other product down here below, the hydroxyl group attached to the central carbon, and the hydrogen attached to the terminal carbon. So here is Markovnikov's rule. The carbon of the hydrogen atom being added to the double bond. So what happens here is that those that already have a hydrogen will gain another hydrogen. All right? So, looking at this hydrogen, do you think it will attach here on the central carbon, or do you think it'll attach on the terminal carbon here? Them that has gets. So the terminal carbon already has two hydrogens attached to it. So any additional hydrogen is going to attach more predominantly on that carbon. So that's what happens. This one up here is a minor product. This is not formed in the majority. It is a minor product form because we show the hydroxyl group attached to the carbon that already has two hydrogens attached to it. The product here below, we put the hydroxyl group on the central carbon and we put the extra hydrogen on the terminal carbon. And that's the way this is what the major product is. Them that has gets. The hydrogen will go to the carbon that has already the most hydrogen. That's the Markovnikov rule, and this is called a Markovnikov addition. And you need to memorize that. I can't stress it. This will come up over and over again throughout the semester. Markovnikov addition or Markovnikov rule. And so then you're probably thinking, well, give me another example. Or what happens if the carbons have the same number of hydrogens? All right, so let's look at that. What do you think? What do you think happens if I take something that looks like all right, so we got this. We do that, and we'll put a double bond here, and a hydrogen here, and a hydrogen here, and a methyl group here. All right. So, well, let's just go and fill out the hydrogens. All right, and we're going to add water to that. All right, so what happens? Well, you know the water, and I didn't write this as structural this time. So you'll see that as we move through this, we're not going to keep writing all the structural. Make sure you add the hydrogen ion, though. That's a crucial part. This has to be present. This catalyst has to be present for this reaction to happen. So when we add water to this compound, what's the name of this compound? Two butene, 4 carbons, 1, 2, 3, 4, and the double bond occurs on the second carbon. So 2-butene, we add water to it. It's going to open up the double bond, and you're going to have maybe a hydrogen here and a hydrogen here, and a hydroxyl here, and a hydrogen here, and then a methyl group on the end like so. In this case, you get one isomer. You say, well, I could put the OH on this side and the H on this side. Well, those are superimposable. You can flip one over and it makes the other one, right? So you only get one compound here. You don't get 2 isomers here because they're the same thing. So that does happen. Doesn't matter because these only had 1 hydrogen each. You're not going to see something different there. All right. Now, that doesn't mean you can't have. Yeah, that's a little leading, isn't it? So let's do that. If I change this out and I make this the OH group here, and I change this out and make this hydrogen here, again, we have to number these by the lowest carbon. So this becomes what? 2-butanol. All right. Well, if we go back and make this the hydrogen here and this the hydroxide here, it's still 2-butanol. This now becomes carbon number 2. We get 2-butanol. So we don't get any isomers here because of that. Now we can, I mean, I guess we could make something a little more complex. Let's try something else here. All right, let's try something a little more complicated. Let's try drawing something like what do you want to say? One hexene. How about that? All right. So let's have you draw one hexene. So hexene, 1, 2, 3, 4, 5, 6, 7. Oh, that's just sad. Let's try that. Let's try that better. Let's try a different ink color too. I'm getting tired of red. All right. 1, 2, 3, 4. All right, 2, 4, 6. So there's 6 carbon. 1, 2, 3, 4, 5, 6. All right, and we're going to call this one hexene. All right, so if I do that, it would look like that. Okay, and so we're going to do a Markovnikov addition. So we're going to add to that water. Don't forget your strong acid catalyst. All right. So when we look at this, 1, 2, 3, 4, 5, 6. All right. And so what happens here is we get the OH here and the hydrogen here on this one. All right. Is that the only product we get? No, we would get 1, 2, 3, 4, 5, 6. And on this product, we would get the OH here, and the hydrogen would come off this carbon. All right. So which one of these occurs the most as a product? Is it this one or this one? Which one occurs the most? Well, this one actually had 2 other hydrogens attached to it before we did the addition. And this one only had 1 other hydrogen attached to it after the addition. Well, before the addition, I guess, if you want to think of it that way. So, them that has gets, this one occurs the most. This is the major product. This is the minor product. All right. So the next thing I want you to do is be able to name these 2 compounds. All right. So again, find your longest chain. 1, 2, 3, 4, 5, 6. Look at where the hydroxyl group is. It's on the second carbon. This is carbon 1 up here. This is carbon 2 here. So this would be 2-hexanol. This would be 1-hexanol. All right. Over here, what was this substance? 1-hexene, unsaturated. All right. So I hope you're getting this, but I mean, this is the important part. Markovnikov addition, or Markovnikov's rule, says the hydrogen will attach to the carbon that has the most hydrogen. That will be the major product, and that's what you need to remember about this. All right, let's look at another. Let's look at a ethyne. All right, so ethyne, we have triple bond. All right. So what happens when we add water to this reaction. Well, this breaks open. It's an addition. OH goes here maybe. And the hydrogen goes here. And we actually get a, yeah. So this breaks open. Yeah, let me take this off here. What's interesting about this actually continues on. You could show it as a product with the double bond. Yeah, let me do this over because I think it's probably best to show it this way. I try to go right to the final product. Let's not do that because I think you need to see what happens here. All right, so initially one of the pi bonds breaks and you get a double bond like this. All right, so right now you look at this and you go, oh well, carbon's got 6 electrons around it or 3 bonds, and the same thing about this one, and we know it has to have 4. So for this one we'll say the hydrogen attaches here, and just for looks we'll say the hydroxide attaches here. All right, and you go, well, that looks pretty good. But as the reaction continues, this double bond breaks, and we get 3 hydrogens on this carbon, a single bond to the other carbon. Now watch what happens here. We get a carbon double bonded to an oxygen, and then the hydrogen off the end like so. All right. This reaction actually happens so quickly we can't really do much of a change between here and this part. All right. So then you look at this compound and go, question is, what type of compound is this? You should be able to identify this compound. And the key is going to be, and this is going back to chapter 10, that's why I'm really concerned about chapter 10. As you go back to chapter 10, you must identify this functional group here. All right, so let me clean this up for you because it looks better when you write it something like this. H3C, C double bonded to a hydrogen like that. Does that help? Also, I have seen it written. I'll write it up here. Oops. The hydrogen here. All right. Tell me what type of compound that is. It's an important one. This is an aldehyde. Aldehyde. So we have made an aldehyde by taking ethine, a triple bonded carbon here, opening up that bond, and this is the first step. And so I think they want you to see this step because it happens really quickly. This is we call this isomerizes to this. This is called an enol, and it changes to an aldehyde. And so you need to be able to look at this ethine or something with a triple bond when reacting with water will open up that triple bond, make a single bond, and that's how we get an aldehyde. All right. So and we will talk about aldehydes as an entire chapter on just aldehydes. It's that important. Okay. Another thing can happen here, just to show you something else that can happen. This hydrogen here, we replace it with, and let me erase it here and here and here. And we replace the hydrogen with an alkyl group. Remember R. Again, R can stand for it can stand for just hydrogen. It can stand for a methyl group, ethyl group, so forth. Oops. Yeah, make the two a little bigger. So it can stand for that. So instead we could put an R here, and if this R is anything other than hydrogen, it's no longer, if R is anything like any of these, like a methyl group or ethyl group, this is no longer an aldehyde, it becomes a ketone. Now, you may have heard of ketones before. Probably where you hear it the most is people who are on like an Atkins diet, where they're eating a lot of protein, very little carbs. They start breaking down muscle, and that muscle, when it breaks down, it releases ketones. And you hear ketonedosis, I think it is. I'm not a biologist, but it's and that's where you see this generation of ketones from people who are doing severe diets. The other part about this, you'll hear that ketones do damage to the liver. This stuff is, and most of these ketones have a real distinctive odor, and kind of a gasoline kind of odor, but with some different other odors attached to it. And we'll see that when we get to this chapter on ketones. All right, so this is an addition reaction too, and we've added water. It's formed a compound here called an enol. You may want to know that term, enol. And then that either forms a ketone if this is other than hydrogen, or if it is hydrogen, it's an aldehyde. So with an aldehyde, this side of the molecule can change. Maybe it's 2 or 3 or 4 or 5, 6 carbons long. That's going to change the name of the aldehyde, but it has to have this functional group, this part. Whereas with a ketone, it's pretty much the same functional group, except R there will be anything but hydrogen. All right, let's talk about another type of reaction. See if I can get, okay. The next is the hydrohalogenation reaction. So this is kind of neat in that, so we've been talking about you have to have an acid catalyst in order for a reaction to happen. So we're going back to our friend ethene, because it's easy to draw. And we're going to add a hydrohalic acid, or something like hydrochloric acid, all right? So here's hydrochloric acid. So here's a strong acid, and we don't need a catalyst here because right there's the hydrogen that's in the acid that's acting as the catalyst. So again, this is going to be an addition. It's going to open up the double bond, and we're going to get a hydrogen attached to the carbon, chlorine attached to the carbon, and then our other hydrogens that were already present, like so. All right, so this would be called chloroethane. Chloroethane. And we can do the same thing. Let's do something a little different. Let's look at, let's say if I have butane again. So we'll do CH3, CH2, CH double bonded to CH2. We're going to add to it, let's just add hydrobromic acid. All right, so what do we get for a product here? Well, we get CH3, CH2, C, and then on this carbon, you're going to have the hydrogen, and you're going to have the bromine, And that hydrogen, remember, this hydrogen is this hydrogen. All right. Then on the final carbon, you're going to have the hydrogen from the hydrobromic acid. And there it is. All right. So some of you are going, well, is that the only product can be formed? No, this actually has two products. You could have where this carbon gets both hydrogens, and this carbon gets the bromine and a hydrogen, or I could have put it here. It doesn't matter. All right, either way. All right, so first of all, do these compounds have the same name? That's the question. Do they have the same name? You should say, no, they do not have the same name. What's the name of this compound here? Well, the bromine's on the second carbon, so this would be 2-bromo. And it's 1, 2, 3, 4 carbons long, 2-bromobutane. This one would be 1-bromobutane. All right. So then the next question is, which one of these occurs the most? Which one of these is a major product of this reaction of this butene? This would be 1-butene with hydrobromic acid. Well, then that gets, this one had more hydrogens to begin with. This terminal carbon had more hydrogens to begin with. So the hydrogen is going to attach itself to the carbon that has the most hydrogen to begin with. So this one that is circled is the major product. So that's what you need to learn. This is why the reactions are important. These are addition reactions. Markovnikov's rule says them that has gets, or the rich gets rich, or the rich get richer. And here we see it actually playing out on this reaction. All right. Let's look at one more reaction. This is, I know this is going to be a long video, but I'm going to get done. This is really what we've been doing all along too. So we got the carbon double bond to another carbon. So we've got ethene again here. Well, it's whatever you want. It's whatever these R groups determine what we're looking at. And in this case, this structure is repeating. So you'll see, like, you've got this substance and you got N amount of it, N number of moles of it. And under a lot of pressure and heat or catalyst, it's pressure, it's heat, which sometimes we symbolize like that, and then a catalyst. Oops. All of a sudden we get this linkage. It goes like this. The double bonds open up and you get a long chain of carbons, depending on how many of these units over here that you have. So 2, 4, 6, we'll say we have that many units. And all of a sudden this all just opens up and makes one long alkane, saturated hydrocarbon. All right. So what is this? What is it when we take a unit like this and we add pressure, heat, and a catalyst, and we get this long chain? And it's based on whatever the number of moles of this unit reactant that we have. Well, welcome to polymer. This is a polymer. And that's why I decided to add it to this video and keep it. So a polymer is a repeating structure over and over that forms a long chain. So instead of, a general way to write this type of polymer is you would just say bracket, then you would have this, usually a squiggly line like this, single bonded to the other carbon, bracket, and then this is saying it continues on. And then in here, these carbons are attached to, in this case, we'll say hydrogens. But they could be R groups. I guess I should start doing that. These could be Rs. They could be methyl, hydrogen, whatever. So this repeating unit, this is called a monomer. So hopefully, let's get the terminology down. When you have one of these, this is called a monomer. But then monomers link together to form polymers. And so this is like one of the common, this is probably the simplest way to introduce a polymer. And so if we take ethene, and so these R's are all hydrogens, and we add pressure, heat, catalyst, we get this long chain of repeating units of CH2 bonded to another CH2. So that's the repeating unit. And that's what we have here, right? I put a bracket. Oops, if I put a bracket here and a bracket here, let me erase that other one. So there's one repeating unit, and then here's the next repeating unit, and then here's the next repeating unit. So again, these are monomers. They've linked together. Now they're called a polymer. And we call this polyethylene. So this polymer here, poly, and this is the common name, ethylene. And over here, when it was actually double bonded like this, when we had this compound, which changes over to this is called ethene. So polyethylene. Ethylene, remembers the common name. We would, I guess you'd call it polyethylene if you're going to follow the IUPAC name. All right. Great, great little story on page 387 if you want to read about polymers. If you like polymers, go for it. This is, I mean, there's so much science in polymers. It's really interesting science. It's such a neat field of science that you start with a simple structure and you make these complex structures and they become plastics, like polypropylene. They talk about that on page 387 and what those plastics are used for. Now, you may just not really like plastics, you know, due to environmental concerns, but you know, plastics are here to stay probably, and so this is really neat stuff if you're into the polymers, and there can be both natural and man-made polymers. All right, that's where we'll stop with reactions. I will do one more video on aromatic hydrocarbons sometime in the future. All right, thank you.